Thank you. So we're going to start a new section now. So up to now we've been doing partial derivatives, looking at derivatives of functions of two or more variables, and some of the issues and concepts related to that. So now we're going to look at what can happen with integration. So you're familiar with the process of integration of functions of a single variable from the work you've done last year. So we want to extend that now and generalize that now to functions of more than one variable. Okay, but there are a few different types of integrals that can arise when you're looking at functions of more than one variable. Now, as we have done up to now, we'll concentrate a lot on the two variable case and look at some cases where you're looking at functions of three variables and talk sometimes about the generalization to arbitrary numbers of variables. Okay, but there are a few different types of integrals that can arise. So the first case we're going to look at are these things called line integrals. So this is in section 1.11. So these are the integrals that perhaps look most like the integrals you're familiar with doing of a function of a single variable. Okay, so for functions of a single variable, you're used to seeing expressions like this here, where you're integrating a function f of x, say, from some starting off value of a, x, to some ending value b. Okay. But now when there are functions of, when there are two variables involved, well, this expression, this f of x dx, is an example of what we call a differential form. So the equivalent thing in two variables is something of the form of this L at the top of the page there. So we got a mixture of the differentials dx and dy. Okay, and these are both multiplied by functions depending on the two variables. So we got a p depending on x and y multiplying dx, and a q depending on x and y multiplying dy. And it's this object, this linear differential form, which we can integrate. And we can integrate it along a line or a curve or a path. These terms are somewhat interchangeable, line, curve, and path, although a line suggests it's kind of straight, but in general, it could be a curved line or something. And these paths or curves that we're going to integrate over, they're paths in the xy space, so they're paths in the plane. Okay, so there are a lot more variety of paths in the plane that you can have, as opposed to paths in the one-dimensional variable space for a function of a single variable. That's why integrals of a function of a single variable just proceed from some start point A to some end point B. And there isn't maybe a whole lot to say about how it gets from A to B, because it just has to progress along the number line from A to B. Whereas if you're going across the space of the pair of variables, x, y, that means you're talking about curves in the xy plane. So there's a lot more choice. But straight away we look at an example. Now, when we're a bit more familiar with these things, we'll look at some applications and different kind of meanings and interpretation that can be given to these things. But for now, we'll just look at it as the kind of mathematical idea of integrating the linear differential form along some curve. Okay, so in this example 1.14, okay, we want to integrate the form 10x squared y dx plus 3x plus 2y dy. We want to integrate it along a curve C, where C is a curve in the plane defined by y equals x squared, going from the origin to to 0.11. So C is this kind of rough sketch of how C looks in the plane. Is this curve here? Just a very rough sketch. So it's going from the origin to the 0.11. And this integral is somehow going to sum up the accumulated effect of these two functions. Okay, but the 10x squared y is keeping track as the x variable changes, and the 3x plus 2y is accumulating as the y variable changes. Okay. Now, just as with partial derivatives, we make use of all the techniques and results we know about derivatives of function of a single variable. Okay. And working out partial derivatives essentially just reduces to working out normal one variable derivatives, okay, but treating the other variables as constants and so on. Well, with integrals, we do a similar kind of, we treat them in a similar way. We essentially reduce these line and path integrals, we reduce them to integrals that we already know about, to integrals of a function of a single variable, okay? So on the curve C, we always have that the y variable is the square of the x variable. And by taking the derivative of both sides, we can see that there's a relationship between the two differentials, dy and dx. Okay, so now you need to use the chain rule when you're working out the differential on the right-hand side. It's going to be 2 times x dx. Okay, and then we use both of these. So we then use these substitutions to reduce the original integral, or to rewrite the original integral to an integral of a single variable function. Something that we already understand and know how to evaluate. Okay, so that's what we do. So we have I is integrating along the curve C. So whenever I see y, I replace it with x squared. So this is going to be 10x to the power 4 dx plus 3x plus 2x squared. Whenever I see dy, I replace it with 2x dx. So in total here, well, I've just got some integrating some polynomial, because I can add these two together now, because they're both multiplying the same differential dx. So I would have 10x to the power 4. Then I've got plus 4x cubed plus 6x squared. And that's all multiplying the differential dx. Although sometimes we can omit these brackets here. It's kind of understood when you're writing out integrating all of this dx, the kind of differential is acting on all the parts. Okay, you're integrating over the curve C now, but we're only mentioning the x variable. We've lost any explicit reference to the y variable. So in terms of what's happening to the x variable as you traverse the curve C from the origin to 1, well, the x variable is simply moving from 0 to 1 along the x-axis. So this just becomes the integral from 0 to 1 of 10x to the power 4 plus 4x cubed plus 6x squared dx. So now we see it just as something that we're quite comfortable with, just an integral of a single variable function just between some starting and ending point. And, we can just evaluate that as normal. Indeed, it's, the evaluation is carried out at the end of page 23 there for you. So this integrates to 2x to the power 5 plus x to the power 4 plus 2x cubed. And you evaluate that at x equals 0 and x equals 1. Well, you get nothing at x equals 0, and you just get 5. 5 at x equals 1. Okay, so this integral will evaluate to 5. So that example illustrates the basic idea. Use the information about the curve. And you see, if you're going along a curve, then there will be a direct relationship between the two variables x and y. So if possible, by analyzing the description of the curve, you make a substitution. You can replace one of the variables with its functional dependence on the other variable. So you translate everything into one variable. Equally well, you could have translated this completely into the y variable. You could have said that x was the square root of y, and dx was 1 over 2 times the square root of y dy, and translated the whole thing into the y variable. Now, that would have introduced square roots and so on. It would have been a bit more messy, but you could have done the equivalent thing just by shoving everything onto the y variable instead. So let's look at some of the properties of these integrals, these path integrals. Well, the integration that's working here is still a linear operator. So, you can use the linearity of the integration operator just as we do for functions of a single variable. So an integral of a linear combination of stuff will just be the linear combination of the individual integrals. Okay. So in particular, when you're integrating p dx plus q dy, you can split that up as the integral of p dx plus the integral of q dy. You're also familiar with another single variable fact. So another single variable property which is related to the second property here is that if you integrate from a to b, a function f of x dx, well, that's the negative of integrating it from b to a, f of x dx. So integration carries this sign. It's sensitive to the direction in which you move. So if you move in the one variable case, if you move along the number line in the opposite direction, you're going to get the negative of whatever you get going in the other direction. Well, a similar property holds for path integrals or curve integrals. If C prime is the same curve but running in the opposite direction, so C will be a curve going along there, but well, I'll just lift it slightly off it, but if C prime will be exactly the same curve, but if you run in the opposite direction. So from the end point of C back to the start point of C. Well, if that's the case, then the two integrals carry the opposite sign. Okay, so integrating along C prime will give you the negative of whatever you get by integrating along C. Another single variable property that we know about is if we have three points in sequence, a, b, c, you're integrating some function, f, the integral from a to c of f of x dx, you can think of that as breaking up of the sum of the two subintegrals. So you can first integrate it from a to b, and then finish off the integral by integrating it from b to c. Okay, so you can split the path in the one-dimensional case. You can split the path up into various subpaths, or split the integral of integration up into various sub-intervals, and produce the separate integrals over all of those. Okay, and just look at the accumulated, just look at the sum of all the sub-integrals, and that gives you the total integral. Well, we can do exactly the same thing with path integrals, these curve integrals. If you have, where we go, A to C, yeah? So 2 points in the plane, a start point and an end point. So the integral here on the left, the integral A to C of L, so that's denoting some curve, say, from the start point A to the end point C, not necessarily the straight line, just some curve. Then, if there's some intermediate point, B, well, we can think of first integrating it from A to B, and then separately integrating it from B to C, and adding the two integrals together. Okay? They give you the same thing as integrating it in one step from A to C. And that allows you to break down a given path integral. If the description of the curve splits up into different parts, it allows you to split the overall integral up into its various subparts. Okay, so let's look at this other example here, example 1.15. Okay, so what are we doing here? We're integrating. So what path have we got? We're starting at the origin A. We're going to B, which is over here. But we want to integrate along A to D and D to B, where D is this point down here. Okay. The thing about lecture theaters is they're designed so that voices carry easily. So please keep that in mind. I'm not saying no talking, but mathematical talking is good, and actual whispered comments about how great I am are fine, but keep the level down. Okay, integrating along this curve C. Now C naturally splits up into two bits. Okay, you're going horizontally and then you're going vertically. So it makes sense, if C is this whole curve, to think of it as C1 and C2. And so the integral along C of this L, we want to think of as the integral along C1 of L plus the integral along C2 of L. Because on C1 has the nice description that the y variable is always 0. And so the differential dy is 0 as well, because the y variable isn't changing at all. So that's very simple behavior for y, and the x variable is starting at 0 and proceeds to the value 1. Similarly, on C2, the behavior is kind of reversed. On C2, x is always fixed at the value 1. So x has a fixed value, but then the differential dx is 0 because x isn't changing. X is just a fixed quantity on C2. And the y variable is beginning at 0 and going to 1. So the description of the two parts of C It's different, but it's so that's why we need to split up the integral in order to evaluate it. Okay. So on C1, the linear differential form L, well, you just ignore everything with y in it. So that kind of cuts out everything. L, in fact, is just 0 on C1, because you see there's a factor, it's factor y in the first bit, the 10x squared y, so that rubs out the first bit. And then there's a factor dy in the second bit, so that rubs out the second bit. So that tells you that the integral along C1 of L is going to be 0. Because the thing you're integrating, the linear differential form, is just identically 0 on C1. In C2, what does L look like? Well, you impose the conditions of C2. So the dx is 0. So you completely ignore that first bit, the 10x squared y dx. That's rubbed out because the differential dx is 0. And on the second bit, the x coordinate is fixed at 1. So that just looks like 3 plus 2y dy. And so the integral along C2 of L is the integral, we'll see y is going from 0 to 1 of 3 plus 2y dy. But that is something you're familiar with and perfectly able to handle. So that just integrates to 3y plus y squared, evaluated at 0 and 1, which should just be 4. Yeah. So overall, we can say overall, we have the integral along C of L is going to be equal to 4. Okay. Okay, so that's a property we'll use a lot, that we can split the curve up into subcurves. You know, in particular in the case when it has a natural splitting into subcurves like this, such as this kind of piecewise linear. You can call this curve a piecewise linear curve. The whole thing isn't a straight line, but it's made up of a collection of straight lines. So it's piecewise linear. Okay. Another way these integrals can be evaluated, or can be looked at, is where there's a natural parametrization of the whole thing by a third variable. So let's look at this example, example 16. Semicircular path clockwise. Let's go -1 to 1. And we're going semicircular of radius 1, so we're hitting 1 there. Kind of that thing, but you're going clockwise. So this is the curve C. And we want to evaluate this integral, which is integrating along C of x squared dy minus yx dx. Now, what can you do with this? Well, I mean, one way to approach this, well, because this is the unit circle, we could approach this as saying x squared plus y squared is always 1. And you could make y be So y then would be the square root of 1 minus x squared. We're looking at the positive half of the circle, so it'd be taking the positive y value, so it'd be taking the positive square root at each point. So that would allow you to get rid of all the y's and substitute them for x's. However, working out the differential dy, well, you can still do it, but you've got some complicated chain rule to do here. Because to get the differential dx out, you see x is buried in there. So it's going to be, you're going to have minus 1 over the square root of 1 minus x squared multiplied by minus 2x and then finally by dx. So we'd have to replace the differential dy by all of this here. Well, not so nice. I don't particularly want to do that, but there's maybe a more natural way to describe a circle, perhaps a bit better, and let's use the idea of polar coordinates in a way, okay? So what we do is we parameterize C by a variable t, by a parameter t, so we can have x as cosine of t, y as sine of t. And what does t have to do in order to describe this? Well, it has to start, so we're thinking of t as an angle, has to start at the angle pi and then go down to 0. That will start you off at this point here on the unit circle, and as t decreases from pi down to 0, this point here will be t equals pi over 2. This is t equals pi. By the time you get this point here will be t equals pi over 4, and then you'll be down to here at t equals 0. That's called a parameterization of the path C. It gives you these cosines and sines. Well, we know about those. We know how they behave. And we can also find expressions for dx and dy. Taking the differential of both sides of the x equation there will give you dx as minus sine of t dt. And doing the same for dy will give us as cosine of t dt. So we can bung everything into I and maybe translate it all to t. Translate everything into the single variable t, and then we'll be able to evaluate that using what we know of functions of a single variable, okay? So we can try translating I into t. Think of it like translating from one language into another. The moment it's in the language x and y, we want to translate it to the language t. So I becomes the integral where we have to integrate from pi to 0. We're going to integrate cosine squared of t. dy is another cosine of t dt. And we minus y times x. So sine t, cosine of t. Then this multiplied by dx, and dx is minus sine t of t. Sorry. Ran up against the edge of the page there. But I got minus y times x times dx, sticking in my dx there. Well, tidying that up a bit, you can see here you've got a cosine squared and a sine squared there. And they're both multiplying cosine of t dt. And cosine squared plus sine squared is 1, so this will become just the integral of cosine of t dt. Well, we can integrate that. The integration of cosine is the sine function. And we're evaluating sine at the limit 0 and pi. And well, sine of 0 is equal to sine of pi, and they're both 0. So overall, you get 0. Okay, but it shows another way in which you can evaluate these things. And again, you're reducing it to the one variable case, okay, to an integral of a single variable, which is something you recognize and you know how it behaves, and you can evaluate it. Yes, question? Well, yeah, so the question is how to interpret these answers. So at the moment, we don't have a so it isn't just the area under the curve. So for functions of a single variable, the integral between a and b will be the measure of the area under the curve between a and b. We don't have such a direct geometric meaning to these integrals yet. You can give remember a function of two variables gives you some kind of a surface. So you've got some kind of a surface there. I mean, the closest thing to what you're talking about area under curve is if you have some curve in the plane here. So if C is a curve in the plane, so C is in the xy plane, then yeah, you can think of what that curve looks like lifted up onto the surface. So this curve at the top is the curve on the surface, which is kind of like f applied to C, if you like. So f applied to C is on the surface. So there is a kind of a natural area you can think about there, which is the area of this curtain, if you like. You think of this as a curved curtain, which kind of, its bottom traces the curve C and its top traces the curve C, but along the surface, okay? So there are curve integrals or path integrals to give this area, but those are of a special type. And we'll see them. I think we'll see them in the next lecture. We'll look at some examples of those. But that kind of interpretation doesn't fit onto these general integrals of linear differential forms. And you can give various interpretations when you look at it in different contexts. So it depends on what the function f is. It depends on what the functions multiplying the dx and the dy are representing. But we'll start to see some example. Once we've built up the basic theory, we'll look at various applications and look at various meanings that it has in different contexts. Was there a question there? It's gone? Okay. Yeah. Okay. So we'll see these soon. Okay. Okay, well, that was just a quick introduction to our line integrals, and we'll see more of those next time. But I'd just like to return, so we were doing these problems in the previous hour. I'd just like to return to this last one, just to show you that, just to finish that off for you. So this was back dealing with our stationary point material. So what was this about? This was about these parallelepipeds, which is just a fancy name for a box, familiar box, a rectangular box. Okay, and the shape of the box will be determined by these three lengths, x, y, and z. Its width, length, and height. And the surface area, well, what's the surface area of the box? The surface area is the sum of the area of the 6 sides. So you've got a side xz, which is this front face here. But of course, there's 2 of those. There's one at the back as well. There's a side y times z. There's 2 of those. And there's also 2 of the xy, the top and the bottom of the box. That's the surface area. So that's a function of 3 variables. So that's S of x, y, z, isn't it? And the volume as well is a function of 3 variables. Now, the volume of a parallelepiped is simply the product of the 3 variables, x, y, and z. So what was the question? The question was, for fixed surface area, optimize the volume. And by that we mean find the maximum volume. Okay. Well, there are various approaches to this. We could set S equal to some fixed value, S naught, some fixed surface area, and obtain Z in terms of X, Y, and S naught, and substitute into V and proceed. Because we then have V as a function of 2 variables. You see, fixing the surface area imposes a relationship on the 3 variables. They can't all vary independently of one another. If x and y are given, then z has to be determined by the values of x and y in order to give you that fixed surface area. So that would be one way to proceed. But alternatively, we can use implicit, we can keep z in the expressions, but treat it as a function. So z is a function now of x and y. In order for the surface area to remain fixed, z has to depend on the values of x and y. Or you could say x depends on the values of z and y, or y depends on the values of z and x. It just has to be a dependence between the 3 variables. And we'll use implicit differentiation. So we're looking for stationary points of V. So we'll be looking for the zeros of the derivative dv dx. But now, you see, V is now a product of 2 functions of x, because you've got the x here, but the z in turn depends on x. So this will be yz plus xy dz dx. And similarly, the derivative dv dy, again, it's a product of 2 things depending on y. The variable y itself, you can see there, but also the fact that z depends on y. So this is going to be xz plus xy dz dy. So we need to find the locations where these two partial derivatives are 0. But since s equal to s naught is fixed, we know that the partial derivatives dz dx and dz dy, we know that they're equal to 0. Okay, if we think of the surface area as being fixed, it can't vary, so its partial derivatives have to be 0. But if you use implicit differentiation to work out what those partial derivatives are, ds dx, which is 0, so you're differentiating this whole thing with respect to x. Well, if you look at your definition of s, I'll put it down here again. S is 2xz plus 2yz plus 2xy. Differentiating the first bit, we need the product rule because we've got x times z and they both depend on x. So we've got 2z plus 2x dz dx. Differentiating with respect to x in this middle bit, you just have that z depends on x. So we have 2y dz dx. And then here, well, you just have the dependence of x, so that just has 2y. So you can kind of simplify that as bit as a factor 2. You've got z plus y plus x plus y dz dx. Similarly, you can show that ds dy, well, you can just write it down by symmetry, really. It'll be 2 times z plus x. Yeah. Z plus x plus, and when you differentiate with x, you had x plus y, so that'll be x plus y again. X plus y, and then you'll have dz dy. You can work through the details as we did in the first one, or just kind of argue that it has to be that by symmetry, because x, y, and z play exactly the same roles there. But this is 0 as well, of course. So the fact that we have these two expressions equal to 0 means we can express dz dx as minus z minus y over x plus y. And dz dy we get from this equation here, because it has to equal 0. Well, you can forget the 2, so you can divide both sides by 2. So you have minus z minus x over x plus y again. So these expressions now can go into our, where do we put those? We put those into our expressions for dv dx and dv dy up here. We put those into dv dx and dv dy, and we look for the zeros. So substituting these into dv dx and dv dy above, gives us that dv dx. Well, this will be yz plus xy x plus y, and dv dy will be xz plus xy minus z minus x over x plus y. And we're looking for solutions of these things equal to 0. So this pair of things equal to 0, we're looking for the solutions of these equal to 0. Well, we can multiply across both equations by x plus y. And this will tidy up to y squared times z minus x equals 0. That's from the first one. And the second one will give us x squared into z minus y. So the stationary point, the optimization of the volume, occurs when these equations are satisfied. So we now have this. This pair of conditions. Now you can see what the solutions are going to be. There are going to be solutions when x and y are 0. Well, that's what kind of solution is that? That's when the box has 0 extension in some of the dimensions. That's going to be the solution where you've got 0 volume. That's going to be the minimum. It's not really going to be a proper box. It's just going to be 2 sheets stuck on top of each other with the appropriate surface area. So the actual interesting optimum value, the maximum value, occurs when the other factors are 0. So there's a stationary point where z minus x is 0 and z minus y is 0. But of course, that's equivalent to what? If z minus x is 0 and z minus y is 0, then x and y and z have to be the same thing. And that's a cube, isn't it? The box where x, y, and z are all the same. Okay, so as required, we showed the box having maximum surface area is in fact a cube. Okay, everybody's ready to go. I'll see some of you at the tutorial on Wednesday and see the rest of you next week.